Thanks, everyone. I'm in loco Amanda today, as she's not able to make it today. So I'm very pleased to introduce Dr. Simon Kelly, who is a cognitive neuroscientist hiding out in engineering. So Simon got his BE engineering from here in 01 and his PhD from UCD as well in 05. Though he did a lot of work with TCIN as well during that time. He then moved to New York and postdoced in the NKI before postdocing in Columbia and then starting his own lab in City College. So after 10 years in New York, Simon moved back to Ireland. He's the last person to be telling us about decision making, having made that decision. Manhattan to Dublin. But he's got some really great publications and a really great research program. So he's published in Cerebral Cortex, Neuroimage, Journal of Neuroscience, and I guess the peak is a 2012 paper in Nature Neuroscience that was a really nice EEG paper. So Simon's going to give us an overview of his research here today. Thanks.
Thanks, Rob. So, that's why it's important to study decision making, is because sometimes your decisions go really awry. So I'm going to talk about a few different studies that I've done, actually starting with that paper that Rob mentioned there in 2012. And what I've been doing since, looking into generally decision making, but we use electroencephalography to get sort of additional insights into the decision making process that I believe, I hope to convince you can't really get using behavioural data alone. So I'll start off, of course, just sort of defining decision making. There's no one accepted definition, but a good one is that it's a deliberative process that results in the commitment to a categorical proposition. And that's probably my favourite one. There are other definitions that actually require that you execute a behavioural response on the back of your decision, right? So as soon as you actually commit to a decision, you actually act upon that. And many people actually believe that decisions are forged in an intentional framework, meaning that to actually decide on something is tantamount to preparing the action that indicates it or that acts upon it. Broadly, there's two areas of decision making. We can make decisions about things that we sense, see, touch, or feel, for example. See, touch, or hear, for example. So, a perceptually difficult decision might be to actually detect a shark in the water when you're diving. And then on the other side, there are value-based decisions, which you can imagine are just purely based on representations of value or something akin to reward. And a very high-level human decisions might be to do with what to do in college, for example, or what career to choose. And the whole idea of studying the decisions in using EEG and behaviour in a controlled lab is that we hope that the simple things we do actually translate to these really complicated and high-level human decisions. But of course, the way we study them in the lab is very, very reduced. And in fact, if there's one take-home message from my whole talk, it would be that it's very tempting when you're studying decision-making or anything else with humans to use very complicated tasks, because you can, of course, you have the advantage of being able to give humans verbal instructions, which you can't give rodents or monkeys. But I would still say, actually, that you're much better off dumbing down your paradigms as much as possible, and I hope that what I show you will convince you of that. So in the lab, you might study perceptual decision-making, and this would count for monkeys or humans. You basically give some stimulus to a subject and ask them to discriminate something about sensory feature in that stimulus. So a sort of prototypical or canonical example these days in decision making is motion discrimination. So often these clouds and dots are used, and you have to say whether the dots are mostly moving towards the left, for example, versus towards the right. So that's a two alternative forced choice decision. And one way you can have animals or humans indicate a decision like that might be to make a saccade towards one target or another. And then if you're correct, so motion was left and you went left, then you get a reward. Or if you're using a human, I shouldn't say using a human, testing a human, that's it. Then you could use points instead of juice, for example. And then value-based decision-making, you might do a manipulation like this, where the animal or human is faced with pairs of options on each trial, and then they come to learn over time that red is associated with a bigger drop of juice than green, and so they start making, they start biasing their decisions toward the red in accordance with that. Now, as you all know from first year in psychology, decisions in general are just the process of translating sensations into action, generally in the brain, can be sort of usefully broken down into three general stages. First, you just have representation of the sensory events in the environment, and there's lots of evidence that we do have brain areas specialized just for doing that. And then there's this sort of middle stage or level where you actually interpret that evidence or translate it in some way into what's known very generally as a decision variable. Some quantity that you can basically apply a decision rule to in order to actually trigger the appropriate action. And then of course the last stage is to actually prepare and execute that action. And again, something that you would know from elementary experimental psychology would be that one really powerful framework for explaining how the middle stage is done, it comes from signal detection theory, which was I suppose the most famous book about it was written in 1966 by Green and Sweat. And there, the idea is that the sensory information is encoded as basically just an observation in the brain. And you can represent that along a unitary axis. Sometimes it's a bigger sensory impression than other times. And so there's this randomness to it. And if you can represent the distribution of the size or strength of the sensory impression for each of two cases, one where there's no signal and one where there is a signal, giving these two distributions here, then the actual decision process boils down to a very simple thing, which is setting a threshold somewhere along that unitary dimension. And whenever the sensory impression, I'm saying sensory impression, but it could be number of spikes from sensory neurons or something like that, if you want to use something more concrete. The idea is that if on any given trial the sensory impression exceeds this criterion level, then you report, yes, I saw that shark. If it's below, you say, no, you didn't. Sometimes you're wrong, sometimes you're wrong in the two different ways. You can either miss one that's really there or false alarm when there's not something there. And it's a really simple idea, but it's been very powerful. The problem with it, I suppose, in many people's eyes is that, it's very interesting also the fact that even when making the same decision again and again, not only do we vary in what we report about what we're seeing or hearing, but we also vary a lot in when we actually produce the reports. Right? And signal detection theory on its own doesn't actually cater for the timing of decisions as well. And so here we're getting into the kinds of decisions that I'm really interested in, the dynamic aspects, and really, electroencephalography compared to, say, neuroimaging, its main advantage is that it's a high temporal resolution, so you can actually look at dynamics and timing and so on. And so, just talking about really famous theoretical frameworks, when it comes to the timing of decisions as well as the accuracy of decisions, there's a whole class of models called sequential sampling models that all have at their root that the longer you look at something, the better the idea you have of what it is, right? In other words, you accumulate information over time. And so the idea here is that sensory areas represent, there's neurons that prefer leftward motion, for example, and then other neurons that prefer rightward motion. And the difference between those two noisy representations, the noise bit is very important, is actually fed into a neural accumulator, if you like. So that's, it's not coming up here, but there's an integration sign here. Just because I'm from the engineering school, I had to put that in there, and it disappeared. So you never know I was an engineer now. So it's integrated over time, and the idea is that instead of just one criterion like in signal detection theory, you have two bounds, basically. And because it's differential evidence, if you align the axis so that upward means more left than right, then on an actual leftward trial, the top one is correct and the bottom is incorrect. And errors basically happen when this noisily migrating or diffusing process ends up just through stochastic variation hits the wrong bound every now and again. And that's what actually explains the fact that we're sometimes wrong, given any kind of sensory evidence or how strong it is, we're sometimes wrong. And it also explains, the same randomness explains why even when we're correct, sometimes we're faster, sometimes we're slower. It all depends on when this decision variable, which is the cumulative sum of the differential evidence, reaches one bound or the other. Okay. You can even have misses if you time out, if your task is such that you have a deadline. So there's been basically, I don't know, 50, 60 years of modeling using this sequential sampling idea. And I think it was 1960 where the first famous paper invoking this idea was used in mathematical psychology. And in the last 20 years or so, there's been a real step up in the interest in all this. And one of the big things that's happening now is that people are starting to marry behavioral data with neural data. So on one level, you have the dyed-in-the-wool mathematical psychologists who will basically concern themselves with what type of model fits behavioral data best. And the end goal there is basically to look at reaction time distributions coming out of your model versus what they really get and see how close a match it is. And that is the goal, is providing a quantitative description of behavioral data. Right, so how much alike the simulated and real are. And then you have the neuroimaging or neurophysiologists who have been using this sort of technique where they will do the same thing. They'll invoke some task and collect all these responses and their distributions, fit the model, and then the parameters that are fit in the model are then fed into an analysis of, say, your neuroimaging data, functional MRI, for example. And then you'll highlight areas of the brain that are most correlated with those parameters, such as was done in this paper here, Heeker and al. That's actually this 2004 paper. But the thing about this is, where is the validation here of the actual model? Right? When you think about it, it's all a little bit circular, right? The mathematical psychologists will validate their model by basically showing that their model fits the behavioral data better than others, right? And then, of course, there's an infinite number of alternative possibilities for models that could fit, again, better, that they didn't test, and there's always that niggling discomfort there. And then these researchers, they basically assume the validity of the model, obviously, because they use the model just to get the parameters. The parameters are correlated with the voxels and so on. And so they're not testing the validity; they're actually assuming it. And the only time you can actually produce some validation in and of itself is if you actually just get a clear view on the decision process itself. And that's something that's really hard to do. And only recently it became possible in monkeys to do this. Well, it was always possible in monkeys, but paradigm innovations and just the right kinds of data analyses actually resulted in really exciting findings of these very dynamics that decision variables actually produce. So the work of Bill Newsom in particular and Mike Shadlin, who was in Bill's lab before and has really carried this on really far, showed that if you do a motion direction decision, as I explained before, it's a really good example. And then neurons in one area of the brain, MT, have neurons that do just what I said. Some of them prefer leftward motion, and they'll fire a lot when there is leftward motion. Others prefer rightward motion. And if you record from those neurons, that's what they do. If you increase the coherence of the dots, so the number of dots or proportion of them that are moving, so the higher the proportion, the easier it is, then the MT neurons respond more and more if that is their preferred direction. They'll respond less and less if it's against their preferred direction. Right, and that's represented here. and it looks like a sort of a step function, right? The yellow one here is 51% coherence. It's really strong, so it steps up very high and remains elevated as long as the stimulus is on the screen. The red one here is much less coherent, so it's much harder to see, weaker motion, and it's still like a sort of a step response, but it maintains a lower sustained level. So that looks like the evidence itself. If you take the subtraction between the dashed ones here are the ones are what you get when the motion is against the preferred direction of the given neuron. So if you take their subtraction, you can see, wow, yeah, the evidence. The evidence is noisy on a single trial basis, and within a single trial, spiking is noisy in general, just like the diffusion models say. Also, there's a higher mean level for stronger evidence. Then they looked in other areas of the brain, most famously the lateral interparietal area, which is just sort of halfway down the parietal lobe in the monkey, where neurons, if you stimulate them enough, they will actually produce an eye movement. It's like an eye movement planning area. It's also been associated very strongly with attention and now decision making. If you look at what the neurons there do while the monkey's looking at the motion, you see not an increase in leveling off, but actually a build-up over time. So meanwhile, there's nothing actually growing in the stimulus. The build-up actually comes from presumably an accumulation of this sensory signal, right? So if you integrate this over time, you just build and build and build, and the rate at which you build, of course, scales with the evidence strength. The stronger it is, the more fast you build up towards the threshold. And compellingly, if you different trials, they actually indicate their decision at different times. But if for every trial you look at that time and align the neural response traces to that time, so it's called response-locked waveforms, you see that no matter what the level of evidence is, and actually also no matter when you decide, even if you look at fast and slow trials and so on, if you align all of these trials that are different to the point where the monkey actually committed to the decision and then made the eye movement to say, I thought it was left, then there's a basically stereotyped level of firing rate at that very moment. And that's the most compelling evidence there is for a threshold effect, that there is a bound. Right? Not only is there a noisy accumulation of evidence, but also the response is triggered when you hit a bound. Right? And so this is where I enter then, and my colleagues. One thing to get from this is that this is a very simple task, the motion task. So our question was, can we do something like this in humans, or is it just absolutely impossible? The importance should be obvious of why we would want to do this in humans. Of course, we can more readily manipulate different setting conditions for making decisions and have human subjects incorporate a lot of different types of information into their decision-making process and so on. Of course, there are some decisions that are pretty uniquely human. Some decisions that I'm particularly interested in are the ones where you're in a sort of continuous monitoring environment, like when you're driving, and you have to just continuously monitor the proximity of the flanking cars, and when one of them looks like they're going to veer into your lane, put on the brake, something like that. And of course, there's different things like the speed accuracy trade-off. There's how do we incorporate value into perceptual decisions? We'll be more likely to say, I think it was green, when we know that green will give us more juice. Even in an instructional scenario, prior probability, which way to dive for a goalkeeper. The goalkeeper would incorporate what they know about the person taking the penalty, whether they tend to go for the left versus the right. But the way that's incorporated might be a bit different when under speed pressure versus when under perceptual ambiguity, such as when you're trying to figure out, what direction the other team are going in. All these kinds of things are human decisions, and if we can actually directly observe decision processes in humans, then we'll be able to actually study these things. So what I use is electroencephalography. I'm sure everybody is familiar with it, but I suppose its advantage and its problem is that it basically it's the electrical activity recorded on the scalp due to the summed global activity of the entire brain, basically. There's some spatial specificities, for example, if I'm preparing a left-hand motion, you would see something over right motor cortex, versus preparing my right where you would see it over the left. But other than that, the spatial resolution is absolutely awful. But temporal resolution is great. And so this is what we think it is. It's the synchronous activity of aligned pyramidal neurons in cortex. And we record them from many electrodes in the scalp. So the first paradigm that Reverend O'Connell in Trinity and I used to actually study decision making was to get at this continuous monitoring scenario, actually. What we wanted to do was see if, the advantage of EEG should be that, you're measuring globally from the whole brain, right? And as I said at the beginning, sensation to action, that whole chain has 3 major stages. What we wanted to do is see if we could actually isolate signals at each level. And I mean isolate, like really, know for sure that this signal here, that's the accumulating evidence. This one, that's motor preparation. This one is the evidence that the decisions are based on. So the way that we did that was, first of all, select a sensory representation or select a decision, I suppose, where the neural representation we know accords directly with the evidence that should be used for the decision. So one of the most basic things that happens is that if you make a stimulus brighter, neural responses recorded on the scalp or inside the brain are bigger and bigger, right? Visual neurons respond more and more vigorously in the higher contrast the stimulus. So we made that the decision. And in fact, we had subjects just looking at this flickering wheel that was just sitting on the screen all the time. Every now and again, it just gradually faded and then went back up again. And in the first version of this paradigm, we made it really obvious. There's no way you would miss this. The thing all but disappears from the screen and then fades back up again. The reason we gradually faded it was that the whole reason event-related potentials in general are difficult to use and difficult to sort of figure out what parts of them refer to reflect what kinds of computations is that we usually use paradigms where we suddenly put things on the screen, right? It's just in general what we do. But any dynamical system, the brain being the ultimate version of a dynamical system, if you give it an impulse like that, a step function, then there's a lot of sort of just, you really knock it on the head, like the entire thing just goes wild, and so little of that is actually specific to the task at hand. It's just a reaction to something happening on the screen. And then actually trying to find in that mess the stuff, like the electrical deflections on the scalp that actually relate to the stuff the brain needs to make the decision is a nightmare then. Making a gradual change actually gets rid of that impulse response from the dynamical system. And we'll see how that works. In the frequency domain, a flicker produces an oscillation at the same frequency. If you flicker 21 hertz, we did, then you see this 21 hertz oscillation, and it's a really nice visual paradigm, just flickering things, because you can identify on the scalp exactly what relates to the flicker through frequency itself. Anything that's oscillating at 21 hertz, that's the thing flickering away on the screen, and you see this nice spectral peak there. So that's what we chose as a decision. What about the other end then, which is also easy, because none of this is really new. On the other end, there are different signals actually that have been isolated over the years that relate to motor preparation. If you sit somebody down and ask them to just produce left or right movements of any kind in their own pace, preceding those movements, you'll see these typical EEG changes. Some of them spectral. Certain spectral bands that actually change in amplitude. Now, one of them is beta activity, so we use that. And so beta activity, because it's a spectral measure as well, it means that our sensory signal and our motor preparation signal are both defined in the EEG spectrum, right? and they're basically, they're oscillations, and so they're sort of cordoned off in the frequency spectrum of the EEG. And after that, what we could do is just look at the actual bog standards event-related potential, which we derive just by taking the EEG, cutting out snippets with respect to every event of interest, and averaging. And you just get a smooth waveform then where all the noise is averaged out. Just by doing that, nothing fancier than that, absolutely nothing fancier than that. Because we get rid of the non-specific impulse response stuff, we get a clearer view on the decision formation. So here's a time frame of the actual target, right? The contrast goes down. Here's the reaction time distribution. People were very variable. This is over 1.6 seconds. Right, so they were very variable. The steady state potential, its amplitude decreased with contrast, of course. When the thing dimmed, the amplitude of that steady state oscillation went down. And we divided it into fast, medium, and slow reaction times. So we got this distribution, just put two dividing lines there, and took the fast ones, the slow ones, and the middle ones. That's these three colors. So in all cases, it just goes down, of course. And then motor preparation. People use their right hand, so you see this decrease. It happens to be a decrease in beta power that you see when people are preparing. That's great. So this dark red one here, the fast one, you see that the motor preparation, when they were fast, it's when the motor preparation was earlier. When they were slow, the motor preparation was later. That all makes sense. And then in the standard event-related potential, we just saw one thing basically on the scalp, which was a central parietal positive potential that just gradually built over time. And if you look at the time frame here, a stimulus that's just suddenly put on the screen would give a huge event-related potential in this zone here, which we don't see at all because we have a gradual fading instead. All we see is this central parietal positivity that just goes slowly up like this. And dividing by how fast you were, fast, medium, and slow, you can see that the dynamics of the signal closely aligns with that. If you do what they do in the monkey studies and align to the response, right, because of all that variability, you see that in particular motor preparation and this central parietal positivity in the same way seem to reach the exact same amplitude, regardless of whether it was a fast or a slow or a medium trial. Right? And all of these are baselined in the same way here. So this was evidence, we thought, that we've actually isolated the decision variable itself.
Sorry, can I just ask,
okay.
Are you varying the speed of the change in contrast of your...
No, it's even simpler. We actually just have one target type. So like many of the best decision studies will systematically vary evidence strength, make it easier and harder. We can talk more about why we made this so incredibly simple, but I think that it's for that reason that we saw dynamics like this. I think it would be possible to see it if you didn't dumb down your paradigm as much as we did. Because when you think about it, in this scenario, like if you were to miss a target, you would never even know. It's continuous monitoring. You don't even know when to expect them to come up. Of course, they don't miss anything because they're so easy. And the subjects know that. You're just sitting there just going, okay, I'll just keep watching. And then when they see the fading, they just click. And so, a lot of what happens usually, when they make an error, you give them feedback that they were slow or they made an error, then they speed up next and they make some adjustments to their decision process. There's none of that here. They just sit there. They're like this sensory receptacle. They just press the button when they see the fading. And I think it is in that really peculiar case where the actual decision process in the brain itself does fall out as simply as this. And so you can see it so simply on the scalp as well. We did a lot of other manipulations then. We didn't vary the rate, but we varied how far it fades. The fading rate was the same. Sometimes it just faded a little bit and then went back. And of course, subjects missed a lot of those dark blue ones. And the reason why reaction time is so fast for those is that the only trials where they actually even catch those are ones where they accumulate early. And in this case, both the motor preparation signal, which goes down and the central parietal positivity shows this pattern where the solid ones here are when they correctly detected the targets. The dashed ones are where they missed them. And you can see that when they do miss them, it's there's much less motor preparation, right? In all these different conditions, there's also much less of the central parietal positivity, right? So it misses when you fail to reach threshold. And then you can see that the threshold effect is there. Obviously the misses aren't there because there's no response. We also wanted to see just how closely this decision process actually follows changes in evidence. So we manipulated the evidence in another way. Again, we didn't change the rate, but we just put a perturbation basically. This red trace here was intermingled among the regular fading. We sort of faded it a little bit and then increased it and then kept fading it like this. Right? So there's a little kink in the contrast function. And you can see that motor preparation actually follows this. So you're preparing to click as the thing is sort of, once you're getting this inkling that it's fading, you're preparing and then you're relaxing your preparation when it goes back again and then preparing again. And you can see that in motor preparation. You can also see it in the decision, in the central parietal positivity. But if we have subjects do the exact same thing, but this time not make a response, just sit on their hands and count the targets, right, and just report them at the end, 23 or whatever, then we still get the central parietal decision process playing out in the exact same way, following the perturbation in the evidence in the same way. But motor preparation basically goes away because there's no motor responses. And so this is starting to point to the idea that this signal is actually a supermodal evidence accumulator. It's a signal that actually gathers evidence about whatever is relevant at the moment, regardless of the nature of that evidence. And so to look more at that, we did an auditory version of the task, and we can actually track steady-state auditory potentials as well on the scalp. So this sounded like a continuous old phone ringing. It's awful. And every now and again the volume went down, probably giving the subject momentary relief. And you can see that the sensory evidence, the auditory sensory evidence does something similar to the visual sensory evidence. But the decision signal just builds in the same way. Right? The blues here are auditory, the reds are visual. And we have two traces in each because I just divided them into fast and slow. All the same for auditory versus visual, same thing. Even within the visual domain, we could have subjects look out for an increase in contrast instead of a decrease. And of course the evidence will increase, the steady-state visual potential will increase. So this is the evidence versus decrease depending on whether the contrast increases or decreases. But regardless, the central parietal positivity just builds positively in the same way. These ones that are together are actually, these two are the two slow ones, these two are the two fast ones for up and down. And up and down are together basically, it doesn't matter. Basically whatever the evidence currently is, whatever the decision you're doing, this signal will cater for it. We did auditory frequency changes instead of volume, same thing. The only instance where we got rid of the decision signal altogether was when we rendered the change in contrast completely irrelevant, in which case you don't get anything at all. You can see that the steady state evidence signal has an attention effect in this case. Right. And in fact, this paradigm here, in hindsight, we realized it's really useful for a neuroimaging study that we're doing at the moment, but also other questions like, it's a great way to actually dissociate signals that relate to representation of the evidence versus signals representing a decision variable, right? Because this will go in two different directions depending on the decision. This will go in the same direction, and then we're applying this logic in a neuroimaging study now to find where the signal is in the brain. Another thing we're doing for fun is to see whether in this kind of scenario we continuously accumulate, basically, right? So when you think about it, you're sitting in a dark room and there's a flickering thing on the screen, and every now and again it fades. we wanted to know, like, do you just accumulate all the time? Because the subject doesn't know when the targets happen. So in one case we had an inter-target interval of 4 seconds, 7 seconds, or 10 seconds at random. So it was really sort of intermittent, and the subject didn't know when to do it. So do they just continuously accumulate? Obviously they would need to leakily accumulate somehow. So you just forget, if you have any inkling from 3 seconds ago, I think you should discount it, right? Because if it didn't go anywhere, didn't turn into a real target, then you should discount it. That could be modeled as just a leaky accumulator. So we asked, does the brain actually do that in a scenario like that? And do I have? Yeah. What we did was look at let's see. Yes, we looked at the steady state visual potential during the inter-target intervals. In particular, we looked at a moment in time here between targets where the subject should be thinking, oh, there should be a target along now, or there could be a target along any minute now, right? But sometimes there's not, it takes a long time. But we just looked at this sort of area where the subject should be ready for a target. And we basically just divided trials in terms of whether the steady state evoked potential was high or low, because of course it fluctuates. As you watch something that's completely not changing, if you stare at it, of course, your perception of it fluctuates. And we harnessed those fluctuations through the SSVEP. Just sort of took trials where the subject happened to be perceiving it as relatively intense, and other trials where they happened to be perceiving it as relatively dim, just by fluctuations. And using those SSVEPs and to divide the trials, we used a fancy stimulus that my student Isabel Vanegas came up with that had phase reversals to make a really robust SSVEP. Once we did that, we could see that if the subject was looking for an upward change in contrast, like for a given block, they're looking for an upward change in contrast, that's their target. Then, and if in those blocks, when the SSVEP was relatively high, there was an increase in the decision signal here, right? And a decrease if it was if there was a relatively high SSVEP, but you were looking for a fading, right? So basically, without any change in contrast of the screen, the contrast is constant on the screen, just by fluctuations in the internal representation of that contrast, measured through the SSVEP. We can actually see that in a completely decision-dependent way, so depending on whether you're looking out for an increase or a decrease, the abstract accumulator basically, will kink up or kink down in response to a change in contrast in the appropriate direction. So we did other studies. One thing you might ask is, well, so you got these building signals, in this paradigm here, but the evidence was building. So how do you know that really? And it has a shape, I suppose, that's like a quadratic, and the evidence itself is linear. So you integrate a linear and you get a quadratic. Okay, but it was important to actually do something just like the motion task, where you can have evidence that just steps up and then stays constant, so that the decision variable, the temporal integral of this, should build at a rate in proportion with the evidence. We needed to test that. So to do that, we used the motion paradigm, just like the ones I mentioned before, but a continuous version of it. Again, we needed to avoid having something come up on the screen very suddenly. So what we did was have incoherent motion just dancing on the screen, but every now and again a certain proportion of dots moved coherently, and the subject had to detect those and say whether they were in the left or right direction. Again, very intermittent. We had 4 different coherence levels. This is where we did manipulate evidence strength in this case. We had 25, 35, 50 and 70% coherence. And so you can see that people were faster and more accurate. This is a miss rate. And they missed fewer of them when it was higher coherence, as you would expect. And when you look at the central parietal decision signal here, you get this nice build-up again, but the rate of build-up scales lawfully with the coherence. right? And this is locked on the stimulus. These are the same waveforms, but locked this time on the response. And again, you see that they come together at the point where the person does finally commit and click the button. In this case, again, we measured a motor preparation signal as well, and this was useful for looking at the relative timing of abstract or supermodal accumulation versus intentional, abstract accumulation versus motor preparation. And this made waves mainly because even in animal work, all of these really exciting neural response dynamics that accorded so well with the theoretical decision variable, they were all measured in areas like lateral interparietal area that are motor preparation areas. So it led people to believe that decisions are made intentionally always, even if you can cancel an action at the last minute, but still to decide on something is to prepare an action for it. But of course, it stands to reason that in some situations you might want to decide what you're looking at independently of how you're going to act depending on it. So we basically outlined a way to separate these two, like the supermodal accumulation, not tied to any particular sensation or action, and specific motor preparation signals. The way we find these motor preparation signals in a two alternative task like this is we have people put two fingers on a mouse like this, and they'll click, for leftward motion they'll click the left finger of the left hand, and for rightward motion they'll click this one, and that means we can get the laterality over motor cortex we can basically subtract the signals over motor cortex. That's called the lateralized readiness potential. In this study as well, we saw that if you just, regardless of coherence, if you took fast versus slow trials, in fact we split it into 6 bins, we could see that the rate of accumulation in this accumulator signal scaled lawfully with reaction time. So on trials where you happen to be faster, they were trials where, presumably by some internal fluctuation of some kind, the decision variable signal built faster, which was interesting. And you can see that in the stimulus locked and the response locked. We looked backwards in time to see, before going into the target, right? So the subject, of course, doesn't know that the target's about to happen. But we looked at the EEG just before it was about to happen, divided in the same way, so fast and medium and slow like that. And the alpha band activity just before the target happened to be higher for slower trials. We looked at that another way as well. This is just broken out by coherence, but it's the same thing. And this actually shows that this shows evidence for the fact that there are just fluctuations from trial to trial, especially in a continuous monitoring scenario where the person doesn't even know when to prepare to see the target. Of course, there are fluctuations of presumably attentional engagement, and depending on those, they have an impact on the rate of evidence accumulation, even with fixed level of coherence. So, in the last couple of minutes, maybe I'll talk about some more research that I've done into decisions where value plays in. In particular, we actually kept looking at perceptual decisions. In other words, ones where you've got an imperative instructions, basically. If it's a color discrimination, green means left button and red means right button, and that's it. But by changing the relative value of those sensory alternatives, you can change people's behavior. And ultimately, people have to basically make choices on the basis of both, like what they see and what they're worth. And this is important for scenarios like this, where you've got implicit preference for one thing over another, but you're in a scenario where you're supposed to do what you've been asked to do. Right? I'm sure all of you, I'm sure addiction has come to mind for many of you, so it's a potential area where this could be important. So it's been said for a long time that the brain just contains explicit representations of value, just in and of themselves. It's just like it's value for its own sake, and it could be a subjective preference. 50-cent CD versus the glowing CD or something like that for a given person will respond. And there's been lots of neuroimaging work done to show certain brain areas that will basically scale their activation in proportion to how that given subject prefers the glowing CD over the 50-cent CD. Those types of music are really similar, I know. And there's been work in monkeys showing that neurons, again in the lateral intraparietal area actually, will scale in their response magnitude depending on the relative value of two options. So in this study, monkeys were given a red and a green. They figured out that red was worth more, and those red signals, those red targets, when landing in the receptive field of the neuron in the lateral intraparietal area, gave a bigger response than the lower value green ones. We wanted to see if we could see something similar in humans. This was our task. We had the subject was fixate. It was a saccade task, just so it's like the monkey studies. Two targets come up, they're two different colors, green and yellow in this case. Then there's a delay of nearly a second. And then the fixation, which is white there, changes color to one of the two colors in the periphery. And then the subject executes a rapid eye movement towards that color, in this case over to the yellow, as soon as that changes color. And there's a very strict deadline of about 300 milliseconds within which they have to make that action, otherwise they get nothing. In different versions we have different numbers of points connected with green versus yellow. In one version we had 3 that came up in pairs. So that's the sort of thing that we did. And of course we can put green and yellow like this or like this, and a relative value signal on the brain. Again, EEG has terrible spatial resolution, but at least we should be able to see something that relates to the relative value of those two things flip sides on the scalp, depending on whether the higher value is on the left or the right. So that was our trick. The behavior showed that these are reaction time distributions. Dashed are errors, solid are correct. Green are low value, right? So the low value color was the fixation color. And so you can see that high value corrects were a lot faster than the low value corrects. Also, when they made a lot more errors, the green dashed here, they made a lot more errors when the color was the lower value color. And they still went to the higher value target by mistake. They did a lot of those, and when they did those, they were very fast. Different subjects had different strategies. We found some people that did nothing. Like if you plot them on an axis where the difference in error rates, so the fact that you make more errors for low value than high value, is represented here. So the higher up there, the more there's a bias. And the reaction time difference on here, you can see that some people don't really bias at all. Then there's a bunch of what we call opportunists that sort of, judiciously prioritize the higher value color without complete outright selection of it. And then we had 2 extremists up there at the top who basically ignored they didn't even perform a perceptual decision. They ignored the color of the fixation point and just had a premeditated plan to saccade to the higher value color, even though it gave them no points on half the trials. So that was interesting, and something that we're following up. In the EEG, we saw a contralateral positivity with respect to where the higher value was. And we saw that for 3 different pairings, 1 versus 2 points, and 20 versus 50 points, and 1 versus 50 points. And it got bigger the higher the differential in reward. If you look at those, the opportunists and conservatives in groupings like this, the more extremely biased they were towards the higher value, the bigger this contralateral positivity was, and across smoothly across subjects they were highly correlated. So the more bias in their behavior, the bigger the signal was. And we call it the posterior contralateral positivity, or PCP. We showed that even within subjects, if you take all the single trials and measure the PCP and take half of the trials for this subject where they had a big PCP and half the trials where they had a little PCP, then the bias in behavior in those trials that you separated only by the signal, the big PCP had a stronger bias than the little PCP, right? So that says that both across subjects and within subjects, there's a strong relationship between the PCP and bias in behavior. And it's worth noting that the behavior happens sometime later, right? The contralateral positivity happens around 300 milliseconds after the two options come up. Then nearly a second later, as I said, is when they have to actually look at that fixation color change and act rapidly to it. Right, and that happens somewhere out here. So this is far in advance. It's encoding the relative value and then having this really strong bearing on how the decision is biased later on. Is it an attention shift? Well, it doesn't look like anything that's been seen before. There's been no contralateral positivities that actually relate to something being preferred, attended, or higher value in the literature before. Alpha band activity biases depending on your attention, despite the fact that in the same subjects, when we give them just single targets, so there's only one thing to pay attention to, we see this really strong lateralization in alpha band activity, which is a very, very reliable index of spatial attention in humans. There's none in the same subjects for the actual decision task. So it's not, attention is not a big player in this task. So we look at different aspects of this task. Again, the subjects made saccades to a really strict deadline, and it was for the color, it was a color decision, and the value was the values were points gained. In other words, it got 40 points, or it got 50 points, and got nothing if they missed them. So we varied some of these aspects. If we made button presses instead of saccades, the signal was still there. If we made them discriminate shapes, square versus triangle, instead of colors, the signal was still there. And if we made them bias their decisions based on points lost instead of points gained, the signal was still there. And it was a contralateral positivity with respect to the target that was highest priority, the one that's more costly to miss in this case. So it's not an explicit representation of value. I mean, if you were looking at these two things, I think I like the cyan more than the green because I would lose less for that one. As a color, it's friendlier to me. So it's obviously it goes opposite that, and it goes towards strategic prioritization. You can get rid of it if you take away either of two things. If you reduce the value difference. Instead of 40 versus 5 points, which was the extreme value difference we had, we use 20 versus 25 points, it goes away. So does the behavioral biasing. If you keep the same value differences, but now give them all the time in the world, take away the strict deadline, it also goes away. If you intensify that deadline, it's still there. And then you produce extreme behavior, basically, where they really, really strongly prioritize the higher value. And since then, we've done other. I think I should stop there because it's 2:00. This is new stuff. But the take-home message, as I said, I think should be that all of these tasks here were completely whittled down to the simplest form possible. One thing I didn't mention is that we are conducting clinical investigations using paradigms like these now in a few different clinical disorders. And then I can talk more about that after, if you like. And just to acknowledge the people who actually collected the data and who I collaborated with on this. Annabelle Blangero pictured here, and Kibble Jim African worked on the value-based decisions, and Reverend O'Connell was my partner in crime, the perceptual decision and the central parietal positivity decision signal. And these are my funding sources. Thank you. Any questions? Sorry, I went very late there.
Yeah, vague questions. May or may not, maybe already answered in a way. Okay, what relates to, so you were talking about there thinking of implicit preference, and you were testing there and looking at the reward methods and so on. I wonder, would your approach, what would it show just in terms of just preferences that have no specific reward attached to them whatsoever? Because, you were talking about the, liking the 50-cent CD versus the glowing CD, but then you went on to look at specific rewards that are attached to, like explicit rewards that are attached to particular stimuli. So I'm wondering about trying to get at this idea of implicit preference that has no explicit reward attached to it. I know there is a kind of implicit reward mechanism that maybe is based on previous experience and various things like you've gotten pleasure out of 50 cents and found it a little boring, but would you be trying to look at looking at specific, or would you think of trying to look at preferences that you're not assigning a particular value or reward to them?
So it's up to them rather than up to us, basically. Like,
and looking at whether you see any kind of similar patterns, I suppose.
Yeah, it's something that Annabelle has been talking about doing, alright, which we haven't done yet. And the way it's normally done in neuroimaging investigations is, of course, to do separate experimentation where you actually get people to choose between these things, like actually and the best studies actually gives them the CD that they want, to really make it work, And there's other work where, I mean, when you talk about these sort of implicit preferences that don't seem to make any tangible sense. I mean, music is one thing, but as you said, these things can just arise. They're almost habitual nearly in nature. There have been some really interesting studies where monkeys and their dopamine neurons have shown preferences for stimuli in the environment that are associated with more information about rewards that you might get. But they themselves don't do anything. Like they're no good for actually finding that reward or dictating where you should forage to get that reward. And they're just it's just information on its own. But one criticism that I had with that study, and there's been, there was eventually a comment written, is that, they're sort of like we're in this, bistable state always when it comes to value-based preferences, right? Is it ever really the case that something can be 50-50 in any way, right? Like I don't think it exists in the brain. Like that complete equality between things, whether it's value or anything else, how much they require attention or how bright they are. The perfect 50-50 equality doesn't actually exist.
Criterion very fine-grained, if you could just over. Yeah.
Well, so those monkeys basically would have started off just sort of, I don't know what these things are about. They're just telling me whether I'll get a reward or not for a correct decision later. They don't actually give me any information to work with for finding that reward. But I have to look at them. I look at this one, okay. Oh, I got a reward, and then they start associating that with reward, even though the task is structured so that, strictly speaking, it has no bearing on reward. That's not the case in the brain, right? Like temporal difference learning is happening, and it's this thing. It's a noisy process, so there's no way that the monkey can understand that something contains information about getting a reward but has no bearing on getting it.
Just related to that, to follow on, I was interested in the idea of you referring to as that kind of random fluctuation just in perception, and linking to that kind of inexistence of pure quality. I was interested in the idea of perceptual adaptation and how you can have those like really interesting after effects based on continuous exposure, which could theoretically train that random fluctuation. I'm not sure if I'm understanding that properly, but which would that shift this threshold in some way when it comes to decision?
Yeah, if you look over our blocks, if you look at the steady state amplitude, over time you see a really strong adaptation effect. It's just, bog standard contrast adaptation. It just falls, and it has that stereotypical sort of exponential shape that people recorded in monkeys in the 80s and cats. And that's part of it. And the models that I'm now coming up with to actually explain how people are making these target detection decisions under continuous monitoring scenarios actually take that into account by the idea is that once you just click to a target, then you have a clean slate. The subject basically samples what they see, and that they can be confident is a sort of a baseline contrast level, and that gives a null distribution in a way. And then everything after that is z-scored. But the main part of this being that this becomes a local decision then, right? It's based on very recent history of what you think no contrast changes, right? A steady baseline level of contrast. So yeah, I think like adaptation plays in very strongly, but I think that higher level mechanism, that is a very low level mechanism, right? Higher level mechanisms take account of it by essentially, high pass filtering the sensory representation, taking out, looking for more local changes.
And but at the higher level one's completely immune of that sort of adaptation.
Probably not.
Because I think then when you start to talk about value judgments and that sort of stuff, you've got like, well, I might prefer the 50 cent CD, but if I've listened to it 20 times, and on a kind of to a much more extreme.
Yeah.
I just
Yeah, I mean, there's a lot of economic utility theory that actually takes into account people's preferences being influenced by how jaded they are with certain options and so on. Yeah, it's not something I looked at explicitly. So.
Just super fast. Where is the CPP in the brain?
It's in actually the interparietal area. It turns out. So we do have the neuroimaging study that I just sort of cast aside because it's just neuroimaging. But yeah, so it looks like for now. So what we did was we had blocks where subjects are looking for an increase in contrast, somewhere where they're looking for a decrease. We also had auditory increases and decreases. We also had a version where they see, they look for visual decreases and don't respond, right? And then we do a conjunction of the three cases, of the 5 cases basically, because the decision signal should work the same in all those cases. The motor preparation, sensory activity, all those things should all be totally different. And yeah, it looks like it could be like on the roof of the interparietal sulcus, basically. Bilaterally, and it's a kind of because it's one of those cases where it's bilateral, but they're both pointed this way, and so it comes up then as a one blob in the middle on the scalp electrically. Same way that auditory lobe potentials can come from here and here, obviously, but they project up here and we get a unitary blob in terms of electrical distribution.
Yeah, not time. We probably can save this for later. I don't. It's not really
Yeah, so
time.
just
Don't really have
in
time.
terms of time, we might. But if
Yeah.
people want to hang on,
One quick question here.
Yeah, I have a very general question. So the decisions that you are investigating, they're all very closely associated with motor preparation, right? And it seems to me that there's some decisions that doesn't seem to be the case. So let's say I decide to visit Paris in December, right, something like that. So do you think that these are really completely different types of decisions that are really implemented elsewhere in the brain? Or what is the relation between these abstract decisions?
I think the only difference you need is to take away the bound. And if in sequential sampling models, the kind of decision that's open-ended that you don't have to act upon immediately, but you just establish. People think that at a certain point in time, usually some imposed deadline or something, you need to move on. You've decided about parts now, and you've moved on to something else. That's an effective deadline in this scenario. At that point, it's not you're not waiting to cross a boundary. You're just then looking at where the decision variable is. And if it's above 0, it's you favour one. If it's below, you favour the other. But it's still a process of integrating evidence from different sources. So in the parasite, you're combining a lot of different aspects of or factors involved in going what you're missing here and so on. So it's still accumulation, it's still integration.
okay, thanks very much, Simon.